Welcome to Lecture for Research Methods. In this one, we'll be talking about a couple of things about how to choose a statistical test for your proposal study, what to consider when interpreting the results in data analysis, and then also what information you should be sure to include when writing the last two sections of your proposal, the data analysis section and the discussion section. In terms of what to think about when choosing a test, well, it depends on multiple factors, one being the number of dependent variables you're looking at. And if you have one dependent variable, so do these groups differ on how depressed they are? That's that one dependent variable. You're looking at it in one way. You'd be doing univariate analyses. And if you had multiple dependent variables, it'd be multivariate analyses. And now you could have multiple dependent variables but still be doing univariate analyses. If you're saying, okay, I want to know if these people differ on depression and I want to know if they differ on anxiety. Okay, that's two questions, and so it's two separate univariate analyses. If you want to know if a group differs on some combination of depression and anxiety, so if you're looking, it's basically if you're looking at more than one dependent variable at once, only then does it become multivariate analysis. Otherwise, you could just be doing multiple univariate analyses. The nature of the independent variables you're looking at, so the number of independent variables, how many there are, and of your independent variables, how many levels are there. And again, remember, for any independent variable, there will always be at least two levels. And typically the thing is not, oh, is it 2, 3, 4, 5? It's, is it two levels or more than two levels? Once you get past two levels, it often changes the test you're looking at. And then if the independent variable is independent groups variable or a dependent groups variable. So if your independent variable is something where you have two groups and they're clearly different groups, and they haven't been matched in any way, that'd be an independent groups variable, a between subjects variable, or if it's more dependent groups, a within subjects variable would use different analyses. And then if the variable was could be measured on an interval scale, which is usually continuous data, or on a categorical scale, so nominal data. Also the nature of the dependent variables, if they're measured on a nominal scale, ordinal scale, or interval scale, that often influences which test you can use. And also many of the tests we use will assume that the data are normally distributed, but if they're not, oftentimes there are alternative tests you can use for non-normal data. And then last, probably one of the biggest ones for you guys, is the nature of your question, with the kind of, I think, the big divide being, are you looking at a group difference, or are you looking at some relationship between variables? Some, if I know this value on this variable, can I predict a value on another variable? Okay. So with all these different things, different combinations of answers to these questions, you can come up with quite a few different types of analyses. And we do not have time to cover every possible option here. Hopefully you've covered these types of things in previous stat classes, but I'll kind of review the highlights of the most commonly used tests for the most commonly used designs here. Okay, so if you're looking at group differences at one point in time with an interval dependent variable, so some sort of continuous DV, you say, are these groups different on that dependent variable? If you have two unrelated groups, right, so a between subjects independent variable, independent groups, you'd simply use an independent groups t-test. So does this group have more of this thing than this other group? Do they differ? Okay, easy. Now if you have more than two unrelated groups, so more than two levels of the independent variable, then you would use an analysis of variance, or an ANOVA. So hopefully something that's kind of popping in your head as well. Couldn't I just use multiple t-tests? If I have three groups, group A, group B, and group C, I could do a independent group t-test, A compared to B, another one, B compared to C, and then another one, A compared to C. Yeah, you could. The problem is, every time you do a statistical test with null hypothesis statistical testing, you have some chance of making a type 1 error. Right? And so the more tests you do, the more likely it is you'll make at least one type 1 error. Right? So, and the rate at which that probability of making an error increases can be quantified, and there's a formula for it, which I won't make you learn. But that's the family-wise error rate. Okay? And so instead of doing that, you do an ANOVA, which tests differences between multiple groups with one test. Right? Now, whenever you do that, oftentimes it's referred to as an omnibus test. Right? It's this overall test, because if you get when you do an ANOVA and you have these three groups and you get a significant F value, hey, yay, I found a difference. Well, okay, is A bigger than B or B bigger than C? Well, the ANOVA won't tell you. You have to go back and do pairwise comparisons. And so you think, well, geez, why didn't I do the pairwise comparisons to start with? Wouldn't that have saved time? Well, yeah, but basically you're doing the ANOVA first to prevent that family-wise error rate, and then you only do the pairwise comparisons if your ANOVA is significant. So if the ANOVA is not significant, you don't follow up and do pairwise comparisons. And the idea here being you're less likely to make a type 1 error if you start with that big test and only do a bunch of little tests pursuant to following a significant omnibus test. Now you can add another layer to ANOVA by doing ANCOVA, analysis of covariance. This is for when you want to compare groups on some variable after controlling for some other continuous variable. So maybe you wanted to compare the education of one neighborhood to another after controlling for income. Now you can't really control for a variable like this, but what it does is it changes the data to after accounting for the variability in the DV related to the covariate. So it makes the data look as if everyone had the same level of income, but they didn't really. And this is appropriately used when you're comparing two groups on some post-test score using pretest as a covariate. I think that's a good use. Most of the uses of covariate, I think, are probably not methodologically sound. So unless you have a really strong reason to do ANCOVA, I would shy away from it. Okay, so we talked about unrelated groups. If you have two related groups, and again, here we're talking about one point in time, so we're not talking about pre-test, post-test. That is one related group. We're talking about any other kind of related group. Maybe you're doing a study where you have identical twins, where one half of the twin is assigned to one level of the independent variable, and the other twin is assigned to the other level. Or you did a matched pairs design, where you selected people from a large sample that were identical on some matching variables, and then you randomly assign one to one group, the other to the other group, and you're comparing them, one person compared directly to the other. Not looking at this group versus that group, but individual to individual by group membership. To do that, you'd use a paired groups t-test, also sometimes called dependent groups t-test. If you had more than two related groups, which other than kind of repeated measures designs across time, rare, but could be. And if you did, you would just use a repeated measures analysis of variance or repeated measures ANOVA. Okay, and those were all for if you had an interval, a continuous DV. What if your dependent variable was categorical? Right, so you have a categorical independent variable and a categorical dependent variable, two categorical variables, and you want to know if the value of one depends on the value of the other. Then you could use a chi-square test of independence. Here in this example, the question is there a difference between men and women regarding their preferred method of disciplining children? The chi-square compares observed to expected frequencies, where the expected frequencies are based on the absence of a relationship or the null hypothesis. So if these things weren't related, out of these 40 people, you'd expect 10 in every cell. But here's what's expected, and there's a formula you can calculate to see did the observed values differ significantly from the expected values. Which important to note that chi-square, not a real popular test because it's if you have a large enough sample, it's pretty easy to get a statistically significant chi-square value, even if it's not a really big effect size. So it's not a very the standards aren't very high for that test. It's not a very rigorous test. Okay, what about group differences across time with an interval or continuous dependent variable? Well, if you have one group and you're looking at changes across time, so just simple pre-test, post-test study, right? So you have some group, you measure them on the dependent variable, then you do something to them, measure them again. And again, this would be that paired groups t-test we talked about before, also called dependent groups t-test. And if you have one group at more than 2 points in time, then again you're going to use a repeated measures analysis of variance. With again, if you have 3, 4, or 5 points in time, when that repeated measures ANOVA is going to give you, yeah, there's a significant difference across time, but you won't know, okay, was time 1 different than time 2 and different than time 3, or was time 1 just different from time 3? You have to follow up with post hoc tests, right? And that's true of pretty much any analysis of variance where you have more than 2 groups. You're going to want to say, if I found a significant effect, main effect, interaction, whatever you're looking for, interpretation, post hoc tests we done to compare mean differences to interpret the pattern of results. If you had 2 or more unrelated groups, and this is probably one of the most common designs where people have 2 groups, and it could be where you use random assignment, randomly assigned to experimental group, control group, do a pre-test and then do a post-test, or maybe you have existing groups, so you're doing a non-equivalent control group, pre-test, post-test design, but somehow you have 2 groups and you want to measure them do something to one, maybe do something different to the other or nothing to the other, and then measure them both again at post and see, okay, did one group change more or less or differently than the other? And to do that, you're going to use a type of factorial ANOVA called a mixed design analysis of variance. Now, if you have 2 or more related groups, and this is usually if it's, if you used a match pairs design and then did pre-post with them, or if you just did a fully within subjects design and you had 2 within subjects factors, right? You submitted them, you did pre-post on one treatment and that same group of people pre-post on some other treatment, then you would use two-way repeated measures analysis of variance. So again, repeated measures ANOVA, just a two-way repeated measures ANOVA as opposed to a one-way. And typically, most of the ANOVAs we do, or you do, will be, one way. Well, if you have one independent variable, that's all that one way means. But most people don't say one way. They just say an analysis of variance, and you assume it's one way. Okay. What about if you're interested in the combination of interval or continuous DVs, looking at group differences? Well, then you would need a multivariate analysis of variance. And now sometimes people will confuse, because repeated measures ANOVA is sometimes abbreviated RMANOVA, and multivariate ANOVA is MANOVA. So they only differ by the R, but they're very different things. Multivariate ANOVA and repeated measures ANOVA, 2 completely separate types of analyses. Multivariate ANOVA is whenever you want to know, do 2 or more groups differ on some linear combination of dependent variables. So like we talked about before, if you want to know, okay, do these groups differ on some combination of anxiety and depression, or anxiety, depression, and panic, whatever. So why would you ever want to use this test? Well, some people use it to try to reduce the number of tests they're doing. I'm interested in anxiety and I'm interested in depression. Rather than doing an ANOVA with anxiety and an ANOVA with depression, I'll just do a MANOVA, right? So they're using that idea of, oh, well, I'll do this omnibus test first, and then if the MANOVA is significant, I'll follow up with univariate ANOVAs. And even though you'll see that in published papers, I'll tell you right now, I think that's improper application of the statistical test. Right? You should only use multivariate ANOVA if you have a theoretical rationale for doing so. If you really are interested in, do these groups differ on some combination of these dependent variables? And sometimes this is if, okay, you think, okay, I think these groups differ on some combination of anxiety and depression, and I want to know what's more important in distinguishing, differentiating between these groups. Is depression better at telling the difference, or is anxiety better at telling the difference? Then you should use MANOVA, because when you get that linear combination, one of those variables will have a stronger weight, right? It'll carry more of the load. It'll have a higher beta weight, which will tell you that it did more of the predicting the difference between the two groups than the other one. So if you're interested in that, yeah, multivariate ANOVA. But I would say don't use it as an omnibus test. It's not the same thing as doing an ANOVA following up with post hoc tests. If you're interested in, do these two groups differ on anxiety and do they differ on depression? Those are univariate questions. Then you should be doing univariate analyses. Okay. You might also be interested in linear relationship between continuous variables. So if you just have two variables, then you're doing bivariate correlation, most commonly with the Pearson R. Right? And there are other correlation coefficients for when your predictor and criterion, which is what the two variables are called, instead of independent and dependent variable, we talk about predictor variable, criterion variable. When your predictor and criterion aren't both on the interval scale, it may be one of them's ordinal, they're both ordinal, one's ordinal and the other, maybe one's even categorical. There are different types of correlations other than the Pearson R that you can calculate. I won't go into all the details here. Just know that there are other types of correlation coefficients that you could calculate to look at the relationship between variables. And even if you suspect the relationship is nonlinear, there are correlation coefficients you can use to figure that out. Sometimes you may be interested in multiple predictors in one criterion. And here's where you're looking at multiple regression. Right? So this is where you have some outcome, some criterion variable, and you want to know, okay, I think these things are all important in predicting this, and I want to know maybe which is the best predictor, or I want to know after accounting for all the variability accounted for by this. So looking at predicting suicide ideation, after I take into account family history with suicide, after I take into account depression scores for the last week, I have this other variable, and I wonder how much of the variability in suicidality can this variable account for after I put these other things in. Right? Those are the types of questions you can look at with multiple regression. And there are multiple ways to do it. Two of the most common, stepwise and hierarchical. Stepwise is whenever you basically let the variables, you throw them all in at once and say, fight it out, and whichever one is the best predictor will come out on top, and it'll eat up as much variance in your criterion as it can, and then the next best predictor after that one's taken its share will rise to the top, and so on and so forth. So you can see kind of the relative strengths of the predictors. Or if you have that question of, okay, well, after accounting for the variability accounted for by SES, gender, or whatever, you can force those things in first and then put the variables you're interested in second. And that would be hierarchical regression, where you can specify and these go first, these go second, these go third, however many steps you want to do. If you're interested in multiple predictors and multiple criterion variables, which probably most of you won't be looking at. But if you are, then you're talking about something called canonical correlation. We're looking at combinations of predictors and combinations of criterion variables having relationships with each other, which we won't get into too much detail into that right now. Okay, in terms of interpreting the results of null hypothesis statistical testing, we throw around the term statistical significance a lot, right? People talk about, oh, the p-value is this and alpha is that. Well, what does the p-value mean? Well, a p-value is a value that, whatever software package you're using, most likely SPSS or SAS or Literal, is going to generate. And it's not what some people think it means. It's not equal to the probability of making a type 1 error. What it is, and if you're interested in why, I'd be glad to talk to you later, but otherwise, just trust me, it's the upper level of the probability of making a type 1 error if you reject the null for a given result. However, you can't know the actual probability of making a type 1 error, because to know that, you'd need to know the probability that the null was true, which you don't know. Okay. But in general, what you're doing with the alpha that's generated by a statistical package is you're comparing it to some alpha level that you set a priori. So before you do the test, you say, okay, I'm going to set alpha at 0.05, at 0.01, at 0.001. And sometimes, typically the default is alpha 0.05. Sometimes if you're doing multiple tests and you're worried about family-wise error rate, you'll reduce your alpha. And one of the simplest ways is to take an alpha of 0.05 and divide that by the number of tests you're doing, and the result being, okay, my new alpha is 0.05 divided by 4. Okay, so that's my new alpha. So any result I get has to be that, the p-value needs to be, that small or smaller to say I have a statistically significant result. Okay. Again, what does statistical significance mean? Well, technically, if you're looking at a mean difference, right, so any type of ANOVA or t-test, it says basically that you're confident the difference between these 2 or 3 groups is not 0. It might be 0.01, difference might be 0.0001, but it's not 0. Hey, that's something, right? Maybe. And for correlations, you're saying if you have a statistically significant correlation, you're confident that the correlation between those two variables is not 0, some non-zero number. Right? Which leads me to some of the criticisms of the p-value. Excuse me. One being that in theory, quite frequently, the null hypothesis will be false. Like, the correlation probably won't be exactly 0. The mean difference between 2 groups, even if your independent variable had almost no effect, if it just had the slightest, tiniest effect, well, then the null hypothesis is still not true. Right? So that's a bit of a problem, potentially. And there tends to be an overinterpretation of p-values because people say, oh, it's significant. If it's statistically significant, it's great. But really, how great is it, right? Because statistical significance is this binary thing. It's yes, it is, no, it isn't. And how much did I miss by? I don't know. Yes, it is, no, it isn't. Right? So if you set alpha at 0.05 and you get p of 0.06, is that slightly significant or almost significant? No, it's not significant. If you set alpha at 0.05 and you get p of 0.0001, is that very statistically significant? No, it's not. It's not a degree of statistical significance. It's yes or no. Okay, so given that, how can we improve upon null hypothesis statistical testing? Well, one way is to start reporting effect sizes. And there's a variety of ways to calculate these, but basically it's a way of saying, well, how big of a difference was there? How big of a relationship was there? So some standardized way of reporting, so we can look across studies and say, Okay, when you did it, you got this effect size. When I did it, I got this effect size. And even if you use different instruments, so I measured PTSD with the PCL, I measured it with Mississippi, but we can both report effect sizes based on our numbers that can be directly compared. Oh, this is a bigger effect than that one. Right? And you can't compare p-values across studies. It doesn't make any sense because, again, that's yes or no. But effect sizes tell you the amount of a difference, the amount of effect, which is really especially important. And this kind of goes back to one of the criticism I don't think I mentioned. When you get non-statistically significant results, so p is equal to 0.07, dang, didn't make it. Try to submit that to a journal for publication. Probably not going to accept it. There tends to be a bias in journals toward accepting only studies that have statistically significant results. Because they figure, well, if you didn't find anything, you must have screwed something up. Which, unfortunately, means there may be this thing called the desk drawer phenomenon, where there are all these studies that are in somebody's desk drawer, or desk drawers across the nation in universities, most likely, of studies that said, oh, yeah, we found this didn't work. Well, we couldn't publish it. And so you end up getting this filtering effect where it looks like something maybe works or has an effect or there is a relationship. But if you were able to consider all the evidence, people saying, nope, didn't find it, you say, oh, geez, that the one that got reported, that might have been a type 1 error. So if we can report effect sizes, then maybe journals will start saying, well, even though you didn't quite get statistical significance, it looks like it did say, well, and here's this number we can report that can add to the conversation that then can be averaged in later, which we'll talk about that in a minute, using another statistical technique. So effect sizes, people are encouraged to report those now. It's about in the past decade, big push towards reporting effect sizes and also reporting confidence intervals. And these, one of the nice things about the confidence interval, where you say, okay, here's where we found the mean for this group, here's the mean for this group, and then they can graphically build a confidence interval around both of those, saying, and we're pretty sure, there's some error in our measurement, right? Because whatever we're doing, there's always measurement error. But given the amount of variability in our group, we can estimate that the true mean is somewhere between this and this for this group, and somewhere between this and this and this group. And you can visually see, okay, how much or how little do those confidence intervals overlap. And if they don't overlap at all, geez, then even with the error, if this one measured too high and this one measured too low, or vice versa, there's still a difference there. So that seems like a really reliable difference. Okay, so that's another good thing to report. And that statistical technique I was alluding to would be meta-analysis. People doing meta-analyses, they go back through the literature and they can find all papers that are looking at the same topic, right? The same therapeutic modality or the same correlation between two variables, and they can, and hopefully, if people reported it, they can just take the effect size they reported and they get them from all these studies, and they use meta-analytic techniques to figure out, okay, overall, a way of basically, and this is a gross oversimplification, but basically, what's the average effect size? Right? So then you don't have to go back and read every single study. They can say, we did that for you. We squished all the numbers into one paper, and overall, yeah, there seems to be a very small effect, or yeah, there's a very big effect. Everybody's finding big stuff here. And so one thing that a lot, especially the early meta-analyses, would do is they'd say, okay, here are all the published effect sizes. Now, if we estimated for every one of these published papers, there's another unpublished paper that found an effect size of 0, then what would the average effect size be? Right? So, and again, you can't really guess how many of those desk drawer papers there are, but they can do some hypotheticals and say, even if there are 1,000 papers saying they didn't find it, there's enough that did find it with big enough effects that maybe there's still something there. And the last thing just to mention would be Bayesian statistics, which is a whole another way of looking at statistics that's really different from what you've probably been taught, what I was taught with regards to null hypothesis statistical testing. It has to do with incorporating an a priori assumption about the probability of there being an effect. And I won't go into the details of that, but just know there is a whole nother way of looking at this, which the popularity of that approach has waxed and waned over time, but at some point it may have a resurgence, and you'll have to go back and learn it. Until then, just know there's another way out there of looking at this stuff. Okay, now on to the writing. In the data analysis section, which in a proposal you can just call it data analysis. In a finished paper, this would be the results section, so that's kind of the analog. Things you want to talk about: what test you would use. ANOVA would be used. Pearson correlation coefficient would be calculated. A mixed model analysis of variance would be used. And then what would the test be used for? Be used to see if this is greater than this, see if this is related to this, whatever. An example: a univariate analysis of variance, ANOVA's abbreviation, will be used to determine, so I said what it is, ANOVA, what's going to be used for? Well, it's going to be used to determine if participants' scores on the BDI-2 differ depending on what type of therapy they receive, CBT versus Gestalt. Okay, so often you'll hear me say, in this section, right at the measurement level, in a discussion, right at the construct level. So I'm not saying if participants will be less depressed, more depressed. That's construct. I'm talking about their scores on the BDI, so at the measurement level. So I want to see if scores will differ. Maybe even I want to say, make a directional hypothesis here. I'll say univariate ANOVA will be used to determine if participants' scores on the BDI-2 will be lower if they receive CBT than if they receive Gestalt therapy. However you want to say it, just make sure you say what the test is and what it'll be used for in terms of how you're measuring the dependent variable. Right? So you need to be naming that tool, that method, that approach for measuring your DV in this section. Okay. So what test will be used for and what result you would expect. So that pattern of results. So an example here, it's expected that participants who receive CBT will score lower on the BDI-2 than will participants who receive Gestalt therapy. Okay. So if I were doing that, I'm using just these very simple measurement, and I could have just used an independent groups t-test. ANOVA does the same thing in this instance. Nothing else is needed. Now, if I had maybe 3 types of therapy, CBT, Gestalt, and maybe solution focused, okay, I'd still use an ANOVA. I'd have to use an ANOVA. I couldn't use independent groups. But if I did that, I'd have to say, univariate ANOVA will be used to determine if scores differ, blah, blah, CBT versus Gestalt versus solution focused. Significant group differences will be examined with post hoc tests comparing mean scores in the BDI depending on group. And then I have to say it's expected that people that get the CBT will score lower than either people that get Gestalt or solution focused, and people that get solution focused will score the same as or higher than those who receive Gestalt. I've got to say the full pattern of what I expect. Okay. And then if you're doing a factorial ANOVA, it gets a bit more complicated, right? Because remember, for a factorial ANOVA, even in the simplest one, a 2x2, you've got a main effect for every IV, so 2 main effects and 1 interaction. So you need to say a main effect of this is expected, or a main effect is not expected, a main effect of the other one is or isn't expected. And then if you expect the interaction, you need to say, however, these main effects, this main effect is expected to be qualified by a significant interaction such that, and then you interpret the interaction, right? So you need to have that full pattern present in your data analysis section, but really probably won't be more than a paragraph for most of you. But do mention, going back to that thing, if I'm interested in, okay, do these people differ on depression and do they differ on anxiety, I've got to talk about both of those. So an ANOVA will compare their scores in the BDI. An ANOVA will also be conducted comparing the scores on the BAI, on the anxiety inventory. So if you're going to measure it, Tell me how you're going to analyze it. If you're not going to analyze it, don't measure it. Take it out of your paper. Okay. In the discussion section, last section of the paper, you need to restate the expected results in plain English. So here's where you go to that construct level, right? Not at the measurement level. So, instead of saying participants will score lower on the BDI, you say participants will be less depressed when they receive this therapy than that therapy. And you want to relate this expected finding to the literature. So it's expected this, and then this would be consistent with so-and-so's finding that CBT works awesome, or this would be contrary to so-and-so's finding that yada yada, right? Throw in something there which you probably will have said in the intro. You're going to pull it back into the discussion, which is again why your paper is kind of like an hourglass, where it starts off broad, gets narrow, and then starts getting broad again, with the discussion intro mirroring each other to some degree. You want to be sure to address anything that might limit or qualify the interpretation of results. So this is the limitations of your paper, right? It's impossible to design the perfect study, and if you did, it'd be really hard to write a good paper. So be sure there's some limitations you can talk about. But when you do so, don't simply say, classic one is, small sample size will be a limitation. Okay, how? Why? You have to say how a limitation would impact interpretation. So small sample size may limit the external validity of the study. Your findings may not generalize to people that differ from this small group of people. Good, that's fine. But don't simply say this would be a limitation. You need to say why or how it would limit your interpretation or impact your interpretation of the findings. You need to identify potential implications or applications of your finding. So if I found what I expected to find, then people should do this differently. Then it would be in line with this theory, or this theory needs to be revised, whatever. So think both at the theory level and at a practice level, like kind of a practical level. What would it mean if you found what you expected to find? If you can't think of anything for that, okay, think about, well, if you failed to find it, what would it mean? Kind of related to that would be what you typically want to end your proposal with, and what most papers end with. What's the next step? Okay, so, and you can do this multiple ways. You could say, if the expected pattern of results is observed, then future studies should da 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 da. And or you could say, if the expected pattern of results is not observed, future studies should da da da. So you think about, if you find what you expect to find, okay, then what's the next step? If you failed to find it, okay, what would you need to go back and fix if you thought, well, this really is an effect, there really is a relationship, but the way I did the study, maybe I wouldn't have found it, maybe I should go back and do this thing differently. And so you're maybe pulling back in something from a limitation. Okay. Hopefully that was helpful. That's all for now. Take care.